Okay, this week we're going to take everything you've learned and we're going to begin to apply it, looking at the whole world. The first thing we're going to do is look at the world, literally. We're going to look at the planetary scale atmospheric circulations. So there are some basic circulations that just because of all the things you've learned that must occur on Earth. So let's look at some of that thought. And think about it. If we had a non-rotating Earth, the sun hits the Earth at the strongest by the equator. That would be the hottest spot. All the air would rise there. Oh yeah, on the nighttime side, there would be the cool air over there, a lot of radiation going on. So you would basically have two circulations. You'd have air coming from the North Pole to the hot equator, rising up, circling back up aloft and back down where it's cold. So, but guess what? Nothing's easy in the atmosphere. We have a rotating Earth. So all those nice little cells we just saw, and remember the Earth Coriolis effect takes into account it, and you wind up with highs and low pressures along the Earth, all due to the wind flow. There's low pressure along the equator. At 30 degrees, on the average, there's high pressure. At 60 degrees, on the average, there's low pressure. So with that in mind, what does that actually look like on today's weather map? Well, let's take a look at today's weather map and see how it looks. 30 degrees is down right around in here. This is a surface weather map, and there is high pressure right across here. So a little bit further north than normal, but it's summertime, so it would be. Again, a little bit further north than normal, but it's summertime out in the west. So you see there is a broad high pressure. Tends to stay right around 30 degrees. It actually drops to the south during the wintertime. You go up to 60 degrees and you can already see 1, 2, 3 low pressures flying around the north, up here in the Northlands, maybe even a little further north than 60 now. So the global circulation is in reality what is occurring. We're in this no man's land, mid-latitude here, where we have some of the high to the south, some of the low to the north. The further north you get, the more lows you're going to see. The further south you get, the more high pressure you're going to see. So the global circulation is actually right there right now. You can actually pick it out in a broad sense of what is happening right now. So with that, let's move on a little ways here. So we just looked at that. We just saw the planetary circulation. So one of the things over the equator as well, you're going to find low pressure. That's the intertropical convergence zone. You saw those winds coming together. That actually will fluctuate north and south depending on where the sun is. It literally will follow the hottest part of the atmosphere where the sun is. So it will move north, and particularly over land we're going to see, and we'll move south again and over the land faster. Remember, oceans, latent heat of oceans, specific heat of an ocean, water is extremely high. It takes an awful lot to heat up. So we're talking here a little bit about subtropical cyclones and all. One of the things to think about, there is subsiding air usually on the eastern sides. So let's look at this a second. If we have subtropical cyclones mainly over the ocean, the eastern side of the Pacific cyclone would be along the west coast of the U.S. And guess what? West coast of the U.S. is relatively dry, especially down here in California and on down. It could be almost desert climate, some of that area. On the western side, on the other hand, there's rising motion on it. So you wind up with a lot more moisture. You think about it. The flow around the high brings the moisture off the Atlantic into the southeast U.S. The flow around the high in California brings down the cooler, maybe a little bit of moisture, but cooler air from North Pacific into California, keeps it relatively cool along the coast, and doesn't bring as much precipitable water to use. So, there's also something called the Hadley cell. Basically, the Hadley cell runs from the equator to 30 degrees north. And basically, you have lots of rising motion around the intertropical convergence zone, lots of thunderstorms typically, and it's going to sink back right around 30 degrees north. If you were a shipper, when we used to do it by sailing, they wanted to be in this trade winds where things would blow out of the east. They didn't like it when they got in the doldrums up at 30 degrees north. If they got up in there, they wound up being stuck. There was no motion to the air. So there is this constant trade wind if you're below 30 degrees north coming out of the east. So if you ever wanted to sail across the Atlantic, that would be a nice way to do it. Aloft, there's a west to east flow. So in the mid latitudes, if you look at today's 300 millibar chart, you see a west to east flow basically. A little bit of a troughiness out here in Idaho, Montana, a little bit of troughiness on the east coast. Lots of high pressure here moving along. And we're going to talk about the beginnings of the monsoon out here in Arizona and New Mexico. We're going to start seeing it here a little bit now. So these are some of the planetary features that you see. And with that, since they're there so much of the time, they develop circulations. One of the things I did want to make sure I re-emphasize, because it's going to be on one of your questions, is the intertropical convergence zone does move more over land than over water. Just because land can cool a lot faster or heat a lot faster. Over the ocean, you see very little motion to it. It moves, but not a lot. But it can really move when it's over the land. So think about these semi-permanent high pressure systems we talked about around 30 degrees north. And guess what? They've been there so long that the oceans follow them. So there was actually a circulation in the ocean that matches up with that high pressure. There's one in the Pacific Ocean. Oh yeah, ever try to swim in the Pacific right along California's coast? It's kind of cool. Well, look where the water is coming out of, the north. Ever want to swim on the east coast of the United States? Look where the water is coming from, out of the south, warmer. So you can see these big highs have actually influenced circulations in the ocean. Monsoons. So if we have these big, broad patterns, some areas of that don't get a lot of change. And there are monsoons that develop. There's monsoons in the Bay of Bengali. We can see up here where summertime it gets very wet in India, lots and lots of rain, but in wintertime, literally the mountains to the north just have cold air coming, dry air coming down, hardly rains ever. So you can see the monsoon pattern developing here. And it gets going and it just stays. It will stay for days. There's an actual monsoon in the U.S. as well. And that's over the southwestern part of the U.S. It's North American monsoon. Basically, it originates with high pressure developing aloft over that area, 30 degrees north. We just saw that high on the 300 millibar. There's low pressure because of the heating that's developing over Mexico. And what happens with that, you wind up getting pressure gradient, and you wind up getting a lot of moisture coming in from the Gulf of Mexico, Caribbean Ocean, even the Southern Pacific into that area during the summertime, and then wrapping back up to the north. So you wind up with a lot of rainfall, much of Tucson's rain, Albuquerque, Phoenix occurs in July, August, into September from the monsoon pattern. And if you were to look at the 300 millibar today, you're actually starting to see some winds coming out of the subtropics, out of the Pacific and up into that area. See them coming across from the Atlantic. There's big high pressure over that area. So you're actually seeing the beginnings of the North American monsoon right now. Okay, moving on here a little faster. We talk about long waves and Rossby waves. Look at the zonal flow. Basically, just a small dips. And if you were to look at our 300 millibar, I would argue that that's almost a zonal flow right now. It's not a big dip down in the atmosphere. In the wintertime, however, if you go back to this chart, look at how deep these troughs can get. And sometimes they go all the way down into the Gulf of Mexico. And think about it. You're pulling cold air in out of Canada. You're pulling warm air up from the tropics, even the Caribbean Ocean. And notice the temperature contrast that's going to be going on in a meridional flow versus a zonal flow. Zonal flows can have lows and highs, but not nearly as strong as meridional flows. And we're going to talk a lot more about that as we move on here. There are blocking patterns that develop with time, and they can really set things up. And we've had a blocking pattern kind of over us right now with this high, and it's been hot and humid for days. The jet stream. Remember, we talked about the contrast in temperature from high to lows. That contrast in temperature really develops right when you get to the tropopause. Think about it. You're warming above the tropopause, but below the tropopause, you're cooling. So there's a tremendous contrast in temperature right there. With that contrast in temperature, you're getting tremendous pressure gradients. That's why your jet stream is always right near the tropopause. Your strongest winds in the atmosphere. And if you were to look at the jet stream today, the jet stream is really way up north, not a lot down over the U.S., but it's moving across Canada. There's some pretty strong winds up here in Canada, 50, 60 knots. Not exactly a great day to want to fly from California to the East Coast and get there quickly, but that's your jet stream up at that latitude. So finally, there's different jet streams. There's a subtropical jet stream in the wintertime that actually comes off of the South Pacific. It can come into California and across the United States. And sometimes the subtropical and the polar jet streams merge. When they do, you can get some of the biggest storms that we get in the United States. Cyclones develop where there's ridge, trough, see winds slow down. You get convergence in there, a loft, so you're pushing downwards, so you're developing high pressure there. But if here winds speed up, you're getting low pressure. So this is the general area you're looking. When you look at this 300 millibars, I would look for low pressure in here. I would look for high pressure back in here. So this is something you're learning again about the total picture of the atmosphere. El Nino and La Nina. El Nino and La Nina are not exactly going on right now. There is a forecast for La Nina. They called it La Nina Watch. So with that, they're forecasting here temperatures to cool, go below normal in the Pacific Ocean. And they already have begun that. And El Nino 3.4 is the region they use. It's in the central and southwestern Pacific. And you can see the temperatures have been trending down, a little bit coming up here lately. So the whole idea is that this is going to continue going and may actually get down cold enough to form a La Nina. A La Nina requires 3 months of at least a half a degree below normal temperatures. One of the other things you can look at is there's all kind of large-scale teleconnections out there. One of them is the North Atlantic teleconnection. There's a PNA, there's an Antarctic, and there's an Arctic teleconnection. By looking at these, you can see these in the global pattern. And when they do form, they have a signal. And right here, North Atlantic oscillation is going to be a little bit negative. If this is in the wintertime, this has a major impact on the East Coast, even into Ohio's weather. So it's something that is very difficult to forecast. We may only get it right about 1 to 2 weeks out, but it can have a major impact on the kind of weather you're going to see in Ohio and in the East Coast of the United States. So I think that's about what we need to talk about on this section. So we'll end it there.